Hello ladies and gentlemen, and welcome to our lesson today. Today we're going to be talking about sketching. I guess I could have written this out before I started my video, but sketching polynomial graphs. So I've decided for today that instead of doing two videos like I have been doing for the other lessons, I'm just going to do one. And I'm going to do that because I feel like trying to squish all of this down into a shorter video would be kind of difficult, and doing examples out of the blue for the people who are only watching the short videos would be kind of awkward. So I'm just going to do one kind of longer video, a bunch of examples, go over everything in depth. Yeah, so if you had a graphing calculator, you could just plug your polynomial into that graphing calculator and it would give you an exact graph. But that doesn't really, it doesn't really do much for us. And plus, we don't use graphing calculators in this class, so we're just going to sketch them. And just a quick reminder for you guys, when we ask you to sketch a graph, we'll give you certain parameters that you need to show, and then basically you're just getting the general shape after that. So say I asked you to graph y equals x squared, and I wanted you to just have an accurate vertex, right? Well, the vertex of x squared is just at the origin, so you could put a dot there, and then pretty much you're just doing the general shape of a parabola. So you don't need any tick marks to say that this is 1 1 or this is 1 1 or that this is 2 4 or anything like that. You can just do the general shape. So yeah, so we're gonna get into it. I'm gonna give you guys a bunch of examples. Yeah, and we'll just get working on it. So when you guys are asked to sketch a graph, there's gonna be 3 steps that you're gonna wanna do. And unlike the last couple videos, these are actually steps. These are not just checks, I promise. So the first step that you're going to want to do is find the zeros. That is a 0, okay. Find the zeros for your polynomial. We'll get into that. I'll explain a little bit more of that later. The second thing you're going to want to do is know what the end behavior, I'm just going to put EB for end behavior. You're going to want to know what the end behavior is of your polynomial. We'll talk about that more later. And then the third thing you're going to want to do is you're going to want to know how many turns it has. And I'll explain what a turn is in a graph and all that good stuff. So say we had the polynomial x squared minus 4. Well, if we wanted to find zeros for it, first of all, if you're asked to sketch a graph for this polynomial, you'll need to find the zeros on your own. But if you ever had the problem where it said find the zeros of find the zeros, it would look like this. It would be set equal to 0. So all we're doing when we're finding zeros is factoring, and we just did we just did a lot on factoring. And so hopefully you guys know that this is a difference of squares, and so we can break this out into x plus 2 and x minus 2. If you don't remember why that works, go ahead and hop over to the older videos and check that out. But so we have x plus 2 and x minus 2, and we know that x squared minus 4, that whole thing, is equal to this whole thing. And since x squared minus 4 was equal to 0, we know that this is also equal to 0. So what we're doing when we're finding our zeros is we're trying to find for what values of x our graph is at 0. So if I were to have a little graph down here, we're trying to know all of the places along the x-axis where our graph crosses. Okay, so there'd be another one right there. So in this graph there would be 3 zeros. Okay, and we'll actually do a graph like this in a minute, but so yeah, when we're finding the zeros, we're finding all of the places where we could put a dot on the x-axis that our line goes through, just for a visual. So now, the way that we would do that, we're trying to say that something multiplied by something is equal to 0. Now, we know that anything times 0, any number times the number 0 gives us 0. So what we're going to try and do is we're going to try and make this equal to 0, this left one, and then we're going to try and make the right one equal to 0. So the way that we do that is we set each of these individually equal to 0. So we'd say x plus 2 equal to 0. And then we just solve for x, so x equals negative 2. And now we'd take our other one, x minus 2 equal to 0, which is equal to x plus 2. Or if you didn't want to put that plus there, that's fine too. So that means for these problems, often there's going to be more than one x value. So if you wanted to write this, you could either write x equals plus or minus 2, or you could put x equals 2 comma negative 2, however you want to list that out. Excuse me. These would be the zeros for x squared minus 4. So I'm going to go ahead and put that up here for our zeros. and we have plus and minus 2. Okay, so that was our first step that we did. We found our zeros, and so the next thing that we want to do is we want to know what the end behavior is for this polynomial. There's kind of a cheat sheet way to remember this that I'll give you guys towards the end, but for now, end behavior, if we look at the greatest power, or the greatest exponent that's in our polynomial, in this case it's this 2 here, okay? If we look at the greatest power and it is even, then we know that both of our, both the end behaviors are going to be the same. And what I mean by the same is they're either both going to be up or they're both going to be down. You're like, Mr. McGill, what's an end behavior anyway? So if we went back to our example we used earlier, y equals x squared, we'll get back to this in a minute. If we go back to y equals x squared, we did our little sketch, right? So this graph, this is an even-powered polynomial, and both its end behavior. So end behavior is we're looking at what the graph does as we go really far to the right and as it goes really far to the left. So as our graph goes really far to the right, it's going really far up. Okay, so that's our end behavior going to the right on this even one would be going up, which would be represented like by this arrow. And as we go really far to the left, our graph is also going really far up. So that's what I meant when I say that they are the same. Every even-powered polynomial is going to be the same in that they are both going up or they are both going down. So this is an example where they're both going up. An example of where they would both be going down would be y equals negative x squared. Negative x squared. Because we know from when we were working with parabolas earlier this year, that when we put a negative in front of it, it just flips our parabola over. So now, when we look at this, as we go really far to the right, our graph is going really far down, and as we go really far to the left, our graph is also going down, which would be an example like this. So, if I were to give you half of your cheat sheet right now for even-powered, I would say that if we have a positive even being the largest power in our polynomial, that our arrows would be like this. Our end behaviors are both going to be up, okay? And then if we have a negative even, being the largest power, they're both going to go down. So we have a positive, and when I say positive or negative, I mean the coefficient of the largest term. So even though there's a negative in here, that won't matter. We're just looking at our biggest term, or the term that's raised to the highest power, so x squared here, so we're only looking at this. This is positive, so we know our end behavior is going to be up on both sides. So the reason that helps us, as I'm sketching our graph, we said that our zeros were plus and minus 2, so if I just did 2 little tick marks here, or I'll do 3 to help us out, okay? So I know that our zeros are at plus and minus 2, and so once I find my zeros, I can as I start sketching my graph, I know that this is good because this is both of my zeros. They're both on there. And now for my end behavior, I can go to the farthest 0 on the right, and because I know as we go really far right on our positive evens, it's going to go up, I can just kind of draw an up part. Okay, and then because we know that our even powers are the same, and because a positive even power on the left also goes up, we can draw something up right there. Okay, so now this last part is what are we going to do between here and here? Well, this is where the number of turns comes in. This is the third part. So the number of turns for a polynomial is determined by its largest power again. So being able to look at a polynomial and know what its largest power is really important, at least for what we're doing right now. So the number of turns is equal to the largest power minus 1. And I can maybe write that out here when I have a little more room in a minute. So our largest power is 2. Okay, so the max number of turns that we can have in this graph is 2 minus 1, okay, which is just 1. And so what a turn means on a graph is a turn is any time our graph is like decreasing or going downhill and then it turns and goes uphill, or if it's going uphill already and then it turns to go downhill. So anytime that like transition from when it's going downhill to going uphill, that would be a turn, or anytime it's going from uphill to going downhill, that's also a turn. So we know that there's one turn in this graph and we don't have any turns yet. So as you guys can imagine, we can kind of just connect the dots with one term there, and this would be like our sketch for x squared minus 4, which was our polynomial. So again, our steps, we found our zeros, which was plus and minus 2. We put those dots on there. Then we knew our end behavior, so we could, from our farthest left and right dots, and when we do problems here in a minute, there'll be maybe 2, 3, maybe 4 dots on our, we'll have 2, 3, or maybe 4 zeros. And so our end behavior, we'll look at the farthest left one and the farthest right one, and we'll draw, okay? And then we looked at how many turns they had, and from that we were able to kind of connect the dots. So this would be my sketch for x squared minus 4. Awesome. So I'm going to leave our steps, and I'm going to leave everything that wasn't only pertaining to that problem. So here's still part of our cheat sheet. And again, this goes to end behavior, or this aligns with end behavior, and then turns, I said I'd write this right here. We go turns equals max power minus 1, okay? And max power being the highest power, okay, of the polynomial. So now if we look at the polynomial, 2x squared minus 32, and we were asked to graph this, the first thing that we would need to do is to find our zeros. The way that we would do this is by factoring this. We said that we're just factoring. So this one has a greatest common factor of 2. I could pull that out. I'm left with x squared minus 16. This again is equal to 0 because this 2x squared minus 32 and 2 times the quantity x squared minus 16, these are equivalent. So because this was equal to 0, this is equal to 0. Now in our parentheses, we have a difference of squares again. So we can go x plus 4 and x minus 4 equal to 0. So now we want to see what we can do to make this multiplication of 3 terms equal to 0. Again, I know that if I have something times something, any 2 numbers times 0, that'll give me 0. So I want to try and make each of these terms equal to 0. Well, if we tried to make 2 0, okay, so let's say we covered up these, we try to make 2 0, we can't just magically make a 2 a 0. So we're just going to forget about that for now, okay? So we're going to look at what's in the parentheses, what we can control with our x's, and again, we'll set this equal to 0. So we have x plus 4 equal to 0, so we get x equal to negative 4, and then similarly to our last one, we have x minus 4 equals 0, x equals positive 4. So just like our last one, we have x equals plus minus a number because we're doing difference of squares. And then this time it's 4 instead of 2. So our zeros on this one were plus and minus 4. So now if I were to start to sketch my graph, we'll have some dots on there now. So say we got our graph. Excuse me. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So we have plus 4, minus 4 as our dots on here, okay? And then again, this one is an even powered, or it is even powered as our greatest power, okay? It's even powered and it is positive. The coefficient in front of our even power is positive. So again, I know that from our farthest left 0, I can draw an up arrow, and from our farthest right 0, I can draw an up arrow. And then also similar to our last one, the number of turns that we can have is our max power minus 1. Our max power is 2, minus 1 is 1. So I know that somewhere down here there has to be this one turn. I drew it like that just so it was kind of like a nice flow. You could, if you're sketching it, you wouldn't be marked wrong if you did it like that. I would just, think it looks a little funny, but, it's up to you guys. It doesn't really matter when you're sketching them. So as long as you have your zeros, you know what your end behavior is, and you know that there is one turn, it doesn't really matter what that one turn looks like. So, and now, hey look, we have kind of a nice smiley face there, right? And then we can put a little nose there, smiley face like that. Anyway, moving right along to our next example. So, this one will be a little different, but not crazy, I promise. So, we have, let's look at x squared. Let's sketch x squared plus 9x plus 8. All right. And you know what, just for fun, no, never mind. We'll leave it like this. So, again, so the first thing we want to do is find our zeros. We're just factoring. This is a Lee-off one, or a backwards FOIL one. If you guys don't remember how to do this, you can go ahead and hop over to the other video, the factoring video from a couple days ago. But for this, we'll go plus x plus 8 and x plus 1. If you wanted to distribute this back in to double check, this is in fact our correct factorization. excuse me, I'm trying to get sick, but man, here we go. So we have x plus 8 and x plus 1 equal to 0. So again, I know that any number times 0 is equal to 0. So I'm trying to make both of these 0, but not at the same time. So I'm going to look here and say x plus 8 equal to 0. I'm going to set that equal to 0 like we did the other time. I'm going to go x plus 8 equal to 0. Well, x equals negative 8. Awesome. And then I have x plus 1 equal to 0. So I have x equals negative 1. So now we have our zeros, which are different. I should have erased this earlier. So now we have a negative 8 for this problem and a negative 1. So if I were to draw my graph, I'm going to draw it a little lopsided so I can get all of my things in here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I have a negative 8, and then I have a negative 1. We're going to look at our end behavior, which again is even. Most of them, most of the ones that we do will be even, but there will be some odd ones, which we will talk about when we get there. But for now, this one is even, and it is positive again, so we're getting lots of practice here. That means that both of these will go up. Also, just like our last ones, the number of terms equals r max power minus 1. 2 minus 1 is 1. There you go. There's our one term. Again, it doesn't matter how this term looks, just as long as it's connected and it looks like, you know, one continuous graph. It's all fine with me. You guys won't get marked down because we're just sketching the graph. So that one wasn't too bad. This next one will be different, and it will be an odd power. So we will get to do something different on our end behavior and on our turns. So that will be good. So this time we're going to look at x cubed plus 2x squared minus 3x. Perfect. So again, we're going through our steps. 1, 2, 3. First step, find our 0. Well, greatest common factor, I can pull an x out of all those terms. So if I pull an x out, I'm left with x squared plus 2x minus 3 equal to 0. And so now, some of you might say, oh, well, I'm done factoring. But actually, this middle part in our parentheses here can be factored further. So leave that x out. Didn't mean to smudge that. Leave that x out. And then we're left with x plus 3 and x minus 1 equal to 0. So this looks very similar to our second example that we did where we pulled out a 2, only now it's an x. So when in that example, when we had our 2, we were saying that anything times 0 gives us 0. So we want to try and make each of these equal to 0. And what we said with our 2 was we couldn't just magically change that 2. Okay, we covered it up like this and we said we can't magically make that 2 a 0, but we can make this x a 0. If x is equal to 0, then we have 0 times, doesn't even matter what we have times, right? Because it's going to be 0. So one of our zeros is going to be 0. I can say that for certain right now. Now we're going to look at our parentheses. So x plus 3. Hopefully you guys are getting the hang of this now. I'll still solve it like this so you can see it. And then x minus 1 equal to 0, x equals 1. If it helps you guys, if you haven't already picked up on the pattern, our zeros are the opposite of whatever we get in our parentheses once we factored. So we have a plus 3 in here. That means that one of our zeros will be negative 3. And then we have a negative 1 in here, so one of our zeros will be positive 1. All right, so now we get to move on to the sketching part of our problem. So we have our 3 zeros. We have 1 at 0, and then we have 1, 2, 3, 4. We have 1 at negative 3, and then we have 1, 2, 3, 4 over here, and we have 1 at positive 1. Obviously, you can tell the accuracy of our sketching is not super important if I'm willing to do stuff like this where it's not even proportionate as we move out. So we've done our zeros. Now we're going to look at end behavior. Now we get to talk about an odd power. So this was our cheat sheet for the evens, okay? And so now what we're going to look at is odds. And when we look at odds, the easiest graph to look at, I'll do a little baby one up here, is the graph of y equals x cubed, because this is to an odd power, okay? So what does the graph of x cubed look like? Something like that. Maybe a little more curvy, but you guys kind of get the point. So with odd powers, we're going to have or I guess if we were to go back, sorry, with even powers, we said that both of them are either going to be going up or both of them will be going down. With odd powers, they will always be different in that one will be going up and one will be going down. If you look at a graph and their end behavior, again, being if one of them as we go to the right is going up and the other one going to the left is going down, just like right here, then you know that it's an odd power. It doesn't necessarily mean that it's to the third, but it does mean that there is an odd power polynomial that we're looking at. So our cheat sheet for our odd ones, a positive odd, just like what we have right here, as we go really far to the right is going to be going up, and then as we go really far to the left, we'll be going down. And then a negative odd, I won't draw this one, but it's going to flip it just like it flipped our parabola. So our parabola, when it was going up like this, we flipped it and then it was coming down this way. So if we were to flip this, we'd be going, instead of going up on the right, we'd be going down on the right, and instead of going down on the left, we'd be going up on the right. Or wow, excuse me. Instead of going up on the right, we'd be going down on the right, and instead of going down on the left, we'd be going up on the left. So if you could imagine, I'll do like maybe a little dotted one, dot, 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 dot. Okay, our negative odd power would look something like that, okay? So now we've got our cheat sheet for our, for all of our, so this is every case, for every polynomial, okay? The highest power can only be even or odd, and the coefficient can only be positive or negative. So every single polynomial that you look at, no matter how big and crazy the power is, you can know what the end behaviors are going to be by this. Or if you guys want to memorize this, if you guys want to, you know, there's lots of ways that you can learn this. I just know it from lots of experience. If you guys want to memorize this cheat sheet, whatever you guys want to do, no matter how big and crazy the polynomial is, one of these cases will be true, and so you can know what the end behavior is. So going back to our problem that we're looking at right now, we have an odd power and it's got a positive coefficient. So we're going to look at the far right 0, which is right here. It's our 1, okay? Our far right 0, and we know that it's going to be going up on the right, so we can just throw an up arrow there. And then we're going to look at our far left 0, which is -3, and we know that's going down as it moves left, so we can just throw a down arrow there. And now, for our number of turns that we're going to put to connect the dots here, it's our max power, which in this case is 3 minus 1, so we're going to have 2 turns, which works out nicely because we need to go, we could go up and then do 1 turn, come through our other 0, and then do a little baby turn right there, a real fast one. And so now we have 1 turn, 2 turns, and we have all of our zeros, and we've done our end behavior. Not in that order, but that's all we've done now. And so now we have this little sketch of what our graph kind of looks like. Now, if you were to have a graphing calculator and you were to graph this, you know, maybe this bump is a little taller and maybe this one's a little shallower. You know, it might look a little different, but like I said, and what I'm really trying to emphasize with you guys for the sketches, stuff like that doesn't matter as long as there is a turn and as long as you have your zeros and as long as you know your end behaviors. So, moving on to our next example. This one's going to be another x cubed. So we're going to have x cubed plus 2x minus 4x minus 8. So this is kind of like the challenge one that I put on the shorter grouping video. We actually did one in class today. You guys seem to handle it really well. So I won't go too in depth with the factoring of this, but it is the first thing that we're going to do because we need to find our zeros. And I'll actually erase our zeros from the last one. So to find our zeros, we're going to do some factoring by grouping. Okay, so I pull out my greatest common factor here, and that should be a squared. So we pull out an x squared, which leaves us with x plus 2. And then we can pull out a -4 from here, which leaves us with x plus 2. If there's confusion on that, either watch the other video, see if it helps you out, or maybe ask me in class. I can go more into why this leaves us with an x plus 2. But it's good that it does because now we can pull this out. We can pull that into the front, okay? And we get x plus 2 times x squared minus 4. Now I should have left a little more room actually because we aren't quite done factoring. This is a difference of squares. And so instead of writing another line, I noticed in one of my other videos right about here is this really bad glare, so I'm going to try and stay away from there. But our x squared minus 4, if we were to factor it, and we actually did it once already in this video, if we were to factor it, is x plus 2 and x minus 2. So we have equal to 0. So here we go. So now we're going to look at what makes this multiplication equal to 0. Okay, so we have x plus 2, x plus 2, x minus 2. So if I were to just do this first x plus 2, hopefully you guys are picking up on the pattern now, that means that we'd have a minus 2 as one of our zeros. This is also x plus 2, so we would get a minus 2, but we don't need to rewrite that. That's only 1 0, okay? And now we have x minus 2, which means that we would have a plus 2 for, for one of our zeros. So now we found our zeros, okay? And this one's a little different from the last one. The last one had an x cubed in the front, and we had 3 zeros. This one has an x cubed in the front, and it only has 2 zeros. So what does that mean exactly? Well, it means you get a little more freedom with your sketching. Okay, so you have plus 2 is one of your zeros, and you have a minus 2 is one of your zeros. We look at our end behavior, all right, so this is an odd one. It is positive, so we go to our far right 0, and we can draw an up. We go to our far left 0, and we can draw down. So now we look at our number of terms, or our number of turns, excuse me. We said that it was our max power minus 1. Well, our max power is 3, minus 1 is 2. So we don't have any other zeros here, okay? And we want to have 2 zeros, or we want to have 2 turns in here between here and here. So some of you might be thinking, like, how do I get 2 turns between here and here if I can't cross the x-axis again? Because in our other one, we went up and then we came down through it and then we went back, okay? So because there are no other zeros in this problem, that means that we can't cross it, okay? We can't cross it again. So we just need to try and connect the dots while having 2 turns. So the way that I'm going to do this, and this is the reason that I said you have a little more freedom here in your sketching. One way you could do this is you can go have 1 turn here, okay? And then your second turn there. So what this does, this touches, so this graph, what it does is it comes up and then it like touches the x-axis and then it comes back down. So that's a turn because we were going from uphill to downhill, okay? And then we go from downhill to uphill, we connect right there. So that's one way you could do it. And the other way you could do it, because there are ways to become more accurate with your sketching and know exactly where it's gonna do this and where it might not. But for our purposes, there's 2 options for your sketching here that would be acceptable. This is one. The second one would be to make it just barely touch that x-axis here, go from, well here, let me draw it. So, and I probably should have dotted that one. So let me do this so that we can tell the difference between the 2 instead of it looking like some crazy graph. So I said this is one acceptable way. The other acceptable way, using our same end behavior, would be to make it just barely touch right there and then curve up and then go here. So both of these have 2 turns. If we're looking at our solid line, we have 1, 2. And then if we're looking at our dotted line, we have 1, 2, okay? So both of them have 2 turns like we want, and both of them touch the axis twice. So either one of these sketches would be acceptable if you were to get a problem like this, where it's an x cubed, and we expect 2 turns, but it only crosses the axis twice. So either of these would be fine for you guys. Sorry if that was a little confusing. Again, ask me questions if you have them in class. Yeah, just let me know. So now, that was that one. So yeah, we're moving on to our next example. I started erasing that without even thinking about what I was doing. So I thought I was gonna regret it, but we're good. So I have x, let's see, this example. Okay, this one will be a little better, I promise. This one won't be quite as complicated. I wasn't expecting that last one to be. Sometimes I make these up in my head and they get a little crazy sometimes, but this one will be better, I promise. So if you were asked to sketch this, first thing we need to do is find our zeros. So we're going to do grouping, and the reason we know we can group is because there's 4 terms here, okay? Set equals 0. So what do these have in common? X squared. So I left with an x plus 1. And so now for my my third and fourth term, I can pull out a -9, which leaves me with an x plus 1. Again, this is good because that means that these are both going to come out in front, and we have an x plus 1 times x squared minus 9. Again, we have a perfect square here, so we can factor it a little more. We have x plus 1 and then x plus 3 and x minus 3. All of that equal to 0. So hopefully, again, you guys are catching on to this pattern now. So if we were to look at just our far left, this x plus 1 here, if we wanted to make that equal to 0, one of our zeros will be -1. If we look at our +3, one of our zeros would be -3. And then if we look at our -3, one of our zeros will be +3. Sweet. So now we're going to try and sketch this out. Got my graph here. I'm going to go, let's go to 4 each side. 1, 2, 3, 4. 1, 2, 3, 4. So I have a -3, I have a -1, and I have a +3. Now we need to look at our end behavior. Again, this is an odd, and it's positive. Now, for all the examples in this video, we've just worked with positives, but there are, there may be, I guess, examples where they are even, and so that's why, or where they are negative, and that is why we included them here. So there you go. So, but now for this one, it's still odd is our greatest power, and it is positive, so we know that from our farthest right dot, we're going to be going up, and from our farthest left dot, we're going to be going down. So now this one is easier to see where the turns are going to be, because like 2 examples ago, we need 2 turns, and we also need to go through the axis right here. So if I were to do this, I'd connect from our far left dot to this dot, or from -3 to -1, and just do a little hill right there. And then to connect from here to there, I'd do that guy. So now we can see again, we have 1, 2 turns. We go from uphill to downhill, that's 1 turn. Then we go from downhill to uphill, that's another turn, 1, 2. We cross through all of our points, which are zeros, so that's good too. And our end behavior is looking good according to our cheat sheet. So this would be a good sketch for this one. Now, the reason, I guess some of you might be wondering, why couldn't I draw, so I'll do a dotted line again. Why couldn't I draw, instead of going up like this and doing a hill and then going down, why couldn't I do something like that? Why couldn't I do the opposite? Well, like I was saying in our last one, if we were to do that, we'd be going from uphill to downhill, that'd be 1 turn. We'd be going from downhill to uphill, that's 2 turns. We'd be going from uphill to downhill, that's 3. So we're already past the max number of turns that we should have, and then we'd be going from downhill to uphill. So we would actually, if we did draw like this, if you were to look at your number of turns, you'd be drawing 2, you'd be drawing 1, 2, but with our end behaviors already drawn in, you're actually drawing 1, 2, 3, and 4. So that's why we need to draw this solid line graph the way it is, and why we needed to do our little hill on top of the x-axis, and then why we dipped down below it the way we did, in case any of you were wondering. There you go. So, guys, that's all I have for you today. I hope you learned something. At the very least, I hope that we know our steps that we're going to go through when we're asked to sketch a graph, and I hope that you guys can take a picture of this either with your mind or with your phone or in your notes or whatever, okay? And remember this cheat sheet for end behavior, because it's helpful for these. It's really helpful for sketching these graphs. And then the turns, also, you know, I don't think it's too hard to remember, right? It's just the max power minus 1. It's really easy to find the max power. Most of the times it'll be just the farthest left term, not always, but most of the time it will be. And then when it's not, you just need to scan and see which, what the greatest power is, and then just subtract 1 off there. There you go. So, that is all I got for you guys. Yeah, I hope you have a wonderful day. Tomorrow we'll be doing some review, I believe. And yeah, so there you go, guys. Have a wonderful night. I will see you tomorrow in class. And yep, that's it. Goodbye.